When we have multi-loop circuits, it's going to be a little bit more complicated. So let's do an example. Let's say that we've got a circuit that looks like this. Now, we have voltage here. We can say this is like 14.0 volts. And let's say that resistor above it is 57 ohms. The resistor in the middle, let's say, is 250 ohms. And the resistor on the right is 25 ohms. And the battery on the right is 6.8 volts. Now, with this problem right here, we know how in previous examples to do series and parallel, but what's in series with what? And what's in parallel? And you look at it carefully and you say, well, these two are not in parallel. These two are not in parallel. They're not in parallel because the voltages are different. The voltage from top to bottom across the 250 ohm resistor is not the same as this voltage because there's this thing in between. And likewise, it's not the same as that voltage because of that other one that's in between. So they're not in parallel. Okay, well, they're not in series either because current flowing this way splits when it reaches a junction up here. And so we have nothing is in series or parallel. There's none of those resistors are in series with any other resistor, and none of those resistors are in parallel with another resistor. In fact, the batteries are not in series with each other, and they're not in parallel with each other. So that makes this a complicated sort of circuit. Well, not really. It's not really that complicated. We had talked about Kirchhoff's rules before. Kirchhoff's rules, the loop rule, if you go around an entire loop in a circuit, then what you've got is the voltage is zero. At a junction, the current into a junction equals the current out of a junction. So let's use that in this situation right here. So let's imagine that we have a current going upwards over here. So I'll call that I1. So I1 goes here, I1 comes from there. Okay. And then let's imagine that there's a current going through the middle. We can call that I2. And we'll say I2 goes down like that. And then let's imagine there's a current over here, I3. Okay, and it goes like that. So what we see is at this junction right here, the current into the junction is I1 plus I3. The current out of the junction is I2. At this other junction down here, the current into the junction is I2, and the current out of the junction is I1 plus I3. Well, those are basically the same equation right there. Okay, now let's do a loop. Let's imagine a loop that starts here and goes around clockwise. Okay, now this is minus and plus. I like to label the resistors. The current always goes plus to minus. I assume the current in the 251 is going down, so that's plus and minus. And the 25, that end is plus, that end is minus, there's plus. Okay, so I like to write down the write down this, and what I normally do is, I cannot do it on this program I'm doing here online, but what I like to do is I like to draw the circuit in one color. I like to draw the current in a separate color. I like to draw the loop I'm using in a third color, and I like to label, maybe even in a fourth color, the minuses and the pluses. Now, students, I tell people to do this all the time. Students dislike doing that, but it really does help. It helps you keep everything straight. Seriously, I've taught this for a lot of years. It really does help to label everything in different colors. Seriously, it helps. Do it. Buy a set of little cheap map pencils and label things in colors. Okay, so for my loop on the left, I started here and I went clockwise. So I increased by 14 volts. I decreased by 57 ohms times I1. I proceeded here. I decreased by 250 ohms I2, and I got back to the starting point, and that was 0. For my other loop, I'm going to start in the lower right-hand corner, and I am going to go counterclockwise. Now, it doesn't really matter. You can do it the other way if you wanted to, but I'm going to do it that way. I'm going to get 6.8 volts minus 25 ohms times I3, which is what I said was going through there, minus 250 ohms I2. Now, what if I had started down here and gone the other direction? What if I had started in the lower left corner and gone in that right-hand loop? What would that have looked like? Well, that means I would have gone from minus to plus on the resistor. So that would have been 250 ohms times I2. And then I would have gone minus to plus, so plus 25 ohms I3. And then I would have gone from plus to minus, minus 6.8 volts equals 0. Well, notice that is exactly the same equation. I just moved everything to the other side of the equation. So that doesn't really change anything. Okay, so that's really the same equation. Okay, I could have done a loop in which I started here and went around the outside, and that would have worked as well. But if you notice, if I use this equation, and that equation, I have 3 equations and 3 unknowns, I1, I2, and I3. I can solve 3 equations and 3 unknowns. So I1 plus I3 equals I2 is one of the equations I had. We have 14 minus 57 I1 minus 250 I2. Okay, I know I'm being sloppy. I dropped the units right there. Okay. 6.8 minus 25 I3 minus 250 I2 is 0. Okay, so I have 3 equations and 3 unknowns. How do you solve 3 equations and 3 unknowns? There are many different ways of solving this. There is diagonalizing a matrix. There's this, that, and the other. There's actually some calculators have routines. You can just enter the values in there, or you can do the brute force method and just substitute up here I2 equals that. So substitute that in there and there. And then do a little algebra, and if you do some algebra, the equations look like 14 minus 307 I1 minus 250 I3 is 0, and then 6.8 minus 250 I1 minus 275 I3 is 0. If I multiply that equation by 11 and that equation by 10, then what I get is 154, and then, but, you know, so I'd get 154 minus 33, 77 I1 minus 2750 I3 is equal to 0. And then I get 68 minus 2500 I1 minus 2750 I3 equals 0. So I just subtract the bottom equation from the top equation, and I get 86 minus 877 I1 equals 0. So I1 is 0.0981 amps. Okay, so I take that and I plug it into my very first equation, which was 14 minus 57 I1 minus 250 I2 equals 0. And what that gives me is that I get 8.410 minus 250 I2 equals 0. And I I2. I2 is 0.0336 amps. Okay, I know that I1 plus I3 equals I2, so that means that I3 equals I1 minus I2. or sorry, I2 minus I1. So that would be minus 0.0645 amps. Okay, what does that give me? That means that in my problem here, I said that was I1, I said that was I2, and I said that was I3. I got a negative I2. What does that mean? It means that really current was really going that way, going backwards in there, which means I'm charging this battery right here is what's really happening. Okay, but that's okay. Even though we guessed the direction wrong in the currents, we still got the right answer. That means we now know that we got negative current going up, which is current going down through that battery. Well, if I find out what's the power supplied, okay, that's going to be I times V. So for the 14-volt battery, power supplied was 1.373 watts. For the 6.8-volt battery, current's going backwards to the battery, so it's negative power supply. I'm charging that battery, 0.3438 watts. Okay, power dissipated. Power dissipated is I squared R. Okay, so for the 57 ohm resistor, that comes out to be 0.548 watts. For the 250 ohm resistor, that comes out to be 0.282 watts. And for the 25 ohm resistor, that came out to be 0.104 watts. If you add up the power supplied and the power dissipated, it all adds up to within 0.001 watts. That's within rounding error. It means we did this right. Okay. And so now I've kind of flown through this example, so you might want to go back through it again and pause the recording now and then to see the individual steps. But this is an application of Kirchhoff's rules. Okay, we had the junction rule and the loop rule. Okay, remember the junction rule, current in equals current out. And for the loop rule, the sum of all the voltages around a loop equals 0. Now, it does not matter which way you go around the loop, clockwise or counterclockwise. You get the same result. It also doesn't matter which loop. You know, I could have done an entirely different loop here. Rather than doing the interior loops, I could have done a loop like that if I wanted to. And then that'd be minus, plus, plus, minus, minus, plus, plus, minus. And so it would have been plus this, minus that, plus that, minus that. Okay, and so that actually would have been a combination of those other two equations that I had for the other two loops. All you need are 3 independent equations to go with your 3 unknowns, and you can solve to get this. Now, the Kirchhoff rule way of looking at things will actually work for every possible circuit. Series and parallel, reduce and return is easier, and so you do that if you can, but the Kirchhoff rules will work for every possible circuit, because this is really what's happening here. Now, some of you all have taken circuits classes and you've used the method of partial currents. I'm fine with that if you know how to use that for a circuit of this sort. That's perfectly fine with me. There's multiple ways of solving these circuits. I just wanted to introduce this way of doing it for you because this is the way the book does it, and this is the brute force method, which always works, and it's really what's happening at the fundamental level. The partial current method is not really what's fundamentally happening. This is what's fundamentally happening, and this works for all possible circuits.